tree species classification is an important issue for land cover studies and forest management. Further, individual tree-level species identification allows for detailed analysis of a forest ecosystem, and as such, a timely and accurate assessment is crucial. Traditionally, tree species data has been collected through either field-based surveying, which is both time-consuming and labor-intensive, or through the interpretation of aerial imagery. Aerial remote sensing offers the ability to cover large areas of land in a relatively short period of time compared to what can be done from the ground. Aerial platforms coupled with hyperspectral cameras have shown to be effective at discriminating between different species of a wide variety of vegetation. However, it has limitations which prevent it from being completely effective. Hyperspectral imagery does not consider the size or structure of the tree. A study by Rudgett et al. Noted that the spectral signature of a tree changed over time as it matured. In their study, they found that a young spruce tree displayed a similar signature as a mature birch tree. As these trees display a similar signature, hyperspectral data alone is not enough to be able to differentiate between the two. While they display a similar spectral response, they have a significant difference in structure. LiDAR is an effective way to differentiate objects based on their volumetric data, while hyperspectral data is useful to distinguish objects based on their material composition. Tree species classification has been attempted a number of times, with new methods continuously being proposed. The following is an overview of the most notable findings. Rudgett et al. Attempted to use hyperspectral and LiDAR information to discriminate between spruce, pine, and birch trees. They were able to obtain an 83 to 86% correct classification. They found that the age of a tree had a meaningful impact on its spectral signature to the point where it led to significant misclassifications. The displayed graph shows the mean radiance for each of the three species. It should be noted that the classification was only done using the spectral information, while the spatial information was only used to remove anything below 1 meter high. Frank et al. Investigated whether using a spectral angle mapper or support vector machine classifier produced better results when classifying vegetation using hyperspectral and LiDAR data. They found that the support vector machine produced the highest accuracy of 83% using only hyperspectral and 92% with the inclusion of LiDAR. Alonso et al. Fused hyperspectral information with LiDAR data and were able to obtain on average an 83% accuracy. Incorporating LiDAR data only increased average classification accuracy by 4.2%. However, for morphologically diverse species such as tall palm, it was able to increase results from 28% to 71%. A method to utilize both the spectral information from the hyperspectral camera and the spatial information from the LiDAR will be developed for classification. The dense point cloud generated by the LiDAR will also be colorized based on the classification results for visualization purposes. Initially, the method will be developed for tree species classification, as there is a readily available dataset. Investigation will also be done on applications where this method may outperform existing technologies, or even applications where this method may work where existing technologies do not. The first half of this project was aimed at identifying whether the currently available software are sufficient for the scope of this project and to determine both the quality and the limitations of the current dataset. This was done through classifying tree species solely on hyperspectral information. Initially, a linear SVM classifier was trained on the dataset with no distinction between species of tree. It was able to, for the most part, correctly identify the locations of trees and accurately classify gravel, plastic, and dirt. There was some confusion between tree and grass. Next, 3 different sets of labels were defined with the inclusion of the 2 most dominant species in this dataset, Eucalyptus and Melaleuca. The 3 label sets created were a per pixel approach, small regions of interest, and large regions of interest. These 3 label sets were then compared using 3 different classifiers, random forests, linear SVM, and SVM. The random forest classifier performed poorly with many misclassifications. These misclassifications were namely for Melaleuca being confused as either grass or dirt. Out of the 3 label sets, the large regions of interest performed the best, where plastic, grass, and gravel were classified for the most part correctly. The linear SVM classifier performed significantly better than the random forest classifier. The large regions of interest set again performed the best. It was able to identify the location of both species. However, again, dirt was incorrectly classified as Melaleuca. It can be seen in the per pixel set that it correctly identified eucalyptus, but misclassified Melaleuca as dirt. It was hypothesized that the SVM classifier would produce the best results. However, this was not shown to be the case. The SVM classifier took significantly longer than the other 2 to train. The large regions of interest results are not included here as the classifier took too long to train. Compared to the linear SVM, it misclassified more eucalyptus as grass. In most of the classification results, Melaleuca was confused with dirt, grass, or both. This potentially was a result of multiple sources. The first being the low resolution of the hyperspectral camera and not being able to distinguish features of the tree. In the image on the left, it can be seen that distinguishing between pixels representing leaves, grass, dirt, or shadow cannot be readily accomplished. The result of this is the high chance that many pixels of dirt or grass were incorrectly labeled as Melaleuca, or the other way around. Melaleuca is also a naturally spread out tree, which can be seen on the right, and as such, when using a region of interest to label one, pixels of dirt and grass would have been included unknowingly. On top of this, it was found that Melaleuca is spectrally similar to grass, which can be seen here. Not only is it spectrally similar to grass, there is a large degree of variance in the spectral response to the leaves, which likely results in misclassification. It was concluded that the use of pre-existing software will no longer be a viable option going forward due to a lack of functionality and freedom, and as such, a standalone application will be created. However, utilizing these software for the purposes of classification has proved valuable for highlighting the limitation, pitfalls, and considerations when classifying hyperspectral data. It has also served to emphasize just how impactful the inclusion of LiDAR data will be on the classification results. While Melaleuca and grass tend to be spectrally similar, spatially, they are nothing alike. With the inclusion of spatial information, the classifier will have the means to readily differentiate between the two. Thank you.